Alright, Railway Engineering, copyrights 2007, Oxford University. Chapter 13, Curves and Superelevation. Introduction. Curves are introduced to the railway track by bypassing obstacles to provide longer, easily transverse gradients to pass railway lines. Obligatory desired location horizontal curves that are provided with the change of direction of the curve. Track required for the vertical curves are provided with the points for the two gradients meet, but the gradients meet level ground to provide a comfortable ride on the horizontal curve. The level of the outer rail is raised to the level of the inner rail. This is known as superelevation. 13.1 Circular curve. This section describes the defined parameters, elements, method of the setting out circular curves, radius, degree. Curves define either in radius or by the degree. The degree of the curve is angle subtended in center of a 35 millimeter or 100-foot chord. The value of the degree of the curve is determined and is included below. Circumference of the circle 2 times pi times the radius. Angle superintendent center of the circle with a circumference of 360 degrees. Angle superintendent of the center of the 35 millimeter chord or degree of curve 360 over 202 pi r 2 pi times the radius times 3 approximate radius in meters 30.5. 1750 divided by the radius in meters. In this case, the radius is a very large area arc of the circle. It's most equal to the chord of the connection with the two ends of the arc. The degree of the curve is given through the following formula. D is equal to 1750 divided by r in meters, and D is equal to 5,730 r in feet. A 2-degree curve with a radius 1750 divided by 2 is 875 millimeters. 875 meters. Relationship with the radius and Vernus curve. The Vernus and perpendicular distance between the medium of the chord and midpoint of the chord and the arc of the circle. The relationship between the radius of the various versaline curve can be established and shown in Figure 13.1. But let the R be the radius of the curve and the curved length of the chord of the V. C be the length of the chord and V be the versatile of the chord of the length. Alright, C is your length of the chord. A is A, C, and D, E begin with two chords perpendicular with a common point B, but the simple geometry can prove that A, B is equal to times B, C is equal to D, B times B, E. Or V equals 2R divided by V equals C divided by 2 divided by C times divided by 2. Or 2RV with equals to V squared, and C equals C squared divided by 4. V is bearing small but neglected, therefore 2RV is equal to C squared over 4V is equal to C, or V is equal to C squared over 8R. And equal 13.1 of VC and A, VC and R is the same meter for the century, but the general equation can be used to determine the vaccine of the chord and radius for the curves is known. Case 1, values of the meters, values in metric units. The formula can be also written with the V equals over 100 equals C squared over the R 8R. When R is the radius of the curve and C is the length of the chord and meters and V is the versiline centimeters or the versiline centimeters is equal to the chord length in meters squared times 100 divided by 8 radius of the 8 times the radius. Or 12.5 C squared, chord length squared divided by the radius of the curve, or equal, or 125 curve squared divided by the radius millimeters. Case 2, the value of the FPS is or feet per second, where R is the radius for feet, C is the chord length, the V is the versatile inches. The formula can be written with the V1 over 12 equal to C1 squared over 8R1, or V1 is equal to 1.5 C squared, C1 C squared R1 divided by R1 using the formula 13.2 and 13.3. The radius for the curve can be calculated once the versatile and the chord length are known. Determining the degree of the curve in the field. Determining the degree of the curve in the field, the chord length with either 11.8 millimeters or 62 feet is to adopt the relationship between the degree of the versatile the curve. This is very simple, but the chord length is indicated below. Versatile on 11.8 chords or meters or 62 feet is adopted. Versatile and equals 12.5 chord length squared divided by radius centimeters. Or D is equal to 175 divided by R, the ratio is specified. The two equations given the degree of the curve of 11.8 core of the determinant as follows, submitting the value of the r equals 12.5 c squared divided by v. D is equal to 1750 over v over 12.5 c squared equal to 170 v over 12.5 times 11.8 squared. Versus 9 on the 62 foot chord, V1 is equal to 1.5 c squared over the R1 in form of formula 3 inches. D is equal to 5,730 divided by R1. The degree of the curve of 62 feet chord can be determined as follows, substituting the value of the R1 equals 5,730 V1 time over the 1 c squared. C squared equals 530 V1, or 1 times 562 squared. V1 is approximately in inches. The important relationships helpful to determine the degree of the curve at any point with measuring the versine, E entering the centimeters on 11.8 meters chord and the inches on a 62 foot chord. The curve can be as many with the degrees of the centimeters inches of the versine with the chord as given above. Or your maximum degree of the curve. The maximum permissible degree of the curve depends on the various factors of the gauge wheelbase of the vehicle and maximum permissible superelevation or other such allied factors. The maximum degree of the maximum radius of the curve permitted by the Indian Railways various gauges are given in 13.1. Or maximal permissible degree of the curve. The broad gauge has a maximum degree of 10, minimum radius of 175 meters, maximum degree on turnouts 8, and 218 minimum radius meters. Meter gauge has 16 max degree on plane track, 109 minimum radius, maximum degree on turnouts of 15, and minimum radius on turnouts of 116 meters. Narrow gauge has 40 maximum degree plane track, 45 minimum radius, maximum degree 17 degrees on the turnout, minimum radius 103. Alright, elements on the circular curve. Then figure 13.2a and AO and BO of the tangent of the circular curve which meet the intersect at the point called O, the point of the intersection of the apex. T1, T2 are the points where the curve touches the tangents and called the tangent points. TP and O2, 1 and 2 are the tangent length of the curve. It is equal to the case of the simple curve. T1 and T2 is the chord, and EF is the versine of the same length. The angle AOB formed between the tangents AO and OB is called the angle of intersection, or angle 1. The angle of the BOO is the angle of deflection of the angle in degrees found in the sum of the important relationships between these elements. 13.2 shows the elements of the curve, the tangent point O1, points OA and B, terminal 1, curve tangent 1 and 2, intersecting apex. Tangent length is equal to O2 equals O2, and OT1 O equals O2, radius of the tangent of the degree of the divided by 2, T1 and T2, length of the length of the chord, 2 R radius sin of the degree divided by 2, length of the curve, 2 pi R over 360 times the degree of the equals the pi R of the radius of the degree divided by 180. 13.1.1 Setting out with the circular curve. The circular curve is generally set out by any of the following methods. The tangent offset method. The offset method is employed with the setting out with the short of the curve length of 100 meters or 300 feet, and generally used with the delay with the current turnout curve. Then figure 3.3, the PQ is a straight element alignment with the T, but the tangent point TB, the tangent point with the curve known radius. Let AA and BB and CC be perpendicular offset from the tangent and can be provided with the value of the offset of O1 equal to C1 squared over 2R. The C1 is the length of the chord of the tangent, similar with the O2 squared. O2 is equal to C2 squared over divided by 2. O3 is equal to C3 squared over 2R. ON is equal to Cn squared over 2R. 3 shows the tangent offsets of the method. PTA, BCD in the inside of the tangent. C1, C2, C3, C4 lengths from A, TA, AB, BC, and TD. Obstruction. The various involved with the laying of the curve of the usual method there with the follow with the extent of the straight line PT, TQ. It will help with the range of the rod. If the TQ is down with the tangent direction, measure the length of the C1, C2, C3 along the tangent direction. Calculate the offsets for the O1, O2, O3 for the length of the formula given above. The simplest Publicity value C1, C2, C3 may be taken in multiples of the 3 or so, measuring the perpendiculars offset O1, O2, O3, set for the ABC, etc. Locate the ABC, etc. on the curve. In this practice, sometimes it becomes difficult to ascend the tangent length beyond a certain point due to the presence of some obstruction, because the offsets become too largely measure accurately with the length of the curve increase. In such cases, the curve is laid with a convenient point within another tangent drawn out of the point for laying with the curve with the further other measure fix the distance of the newly drawn tangent. Long chord offset method. Long chord offset method is employed with lane curves of short length. In such case, the necessary both tangents can be located in the same way, of the distance between them and be measured offsets from the taken long chord figure 13.4 T1 2, tangent 1 and tangent 2 for the long chord for the curve of the radius R. 13.4 shows the long offset card A, B, C, D, E, and G. O1, O2, O13, O3, PQ, R, UV, W, S, and V standard midpoint. Inside curve A, B, C, E, F, G. Tangent 1 and tangent 2. The length of the chord of the C divided into E equals parts T1, A, B, B, C, C, D, etc., which are the parts for the X equals C divided by 8. Let PW in a line parallel along chord. Let O1, O2, O3 of the offsets be taken with the radius R taken points RQ and P. Versus line and V of the length of the chord C is calculated in the formula. The length from the long chord C, the squared 8 divided by the radius ds is equal to T1 tangent 1 tangent 2 squared over divided by 8r. The offsets of O1 from the line PW is calculated with the formula. O1 is equal to x squared divided by 2r equals to rs squared equal to divided by 2r equal to c squared divided by 128r. RC feet is equal to c squared over 128r. If we use the formula 13 form, the value for the perpendicular offsets v1, v2, v3, etc. can be found as follows. v1 is the c squared over the 8r minus c squared over 128r equals 15 over 16 over x times 16 squared. C squared divided by 8r equal to 15 over 16v. V squared, v2 is equal to c squared over the 8r over the minus 2c squared over the 128r. Equal to 12 16ths over the 60 c squared over 8r equals 12 divided by 16 v, and v3 is equal to c squared over 8r minus 3c 2 divided by 128r and equal to 7 16ths times c squared divided by 8r equal to 7 16ths v. During the field work, the first long chord is marked with the ground and length of the measure for these points for the ABC is marked with the dividing a long chord with the 8 equal parts. The value of the perpendicular offset V1, V2, V3, etc. are then calculated with the points A, B, and C as etc. identified on the curve. Quartering the Versailles method. The quartering Versailles method is also playing with a chord short length about 100 meters or 300 feet. The method first for the location of the two tangents T1 and T2 determine the distance between them and the diminished Versailles is calculated by using the formula. V is equal to 125 c squared divided by r in millimeters. Quartering Versailles means is basically your line set out at 62 foot chord, but it's 100 foot tangent 1, tangent 2, A, B, C. B and A, B, C, D, E, F, G. V is measured the perpendicular center point with O along with the tangent, and the T1, T2 are joined with the distance of AT1 measured as AT is almost half the length of the T1, T2 with the Versailles proportional square chord of the Versailles chord and length of the AT1 V4. For laying the curve of the field of the Versailles V4 was measured with the center point of the B on chord AT1, but the position of the point B of the fixed for the similar point is also fixed for the self. The second half of the curve of the AB is further on the subchord. Versailles subchord is measured in V divided by 16. In this way, the D and F are also fixed for the curve can also be then laid by making half chords quartering them Versailles on the half chords. Chord deflection method. Chord deflection method, the laying of the curve is one of the most popular methods for the Indian Railway. The method particularly suited with the confined locations as most of the work is done immediately proximity with the curves. Figure 13.6 let the T1 be the tangent point for A, B, C, and D, and be excessive points over the curve. Let X1, X2, X3, X3, 4 be the length of the curve. The T1, A, B, A, B, A, B, A, B. T1A, AB, BC, and CD for the practice of all the chords in equal length. Let the value of these chords be C. Let last chord may be maybe a different length. Let the value of C1 can be provided. Okay, so you have A, B, and C and D lengths from T1 to A to B, B to C, and C to D. You're inside X1, X2, X3, X4, tangent apex. First offset is A to A, X1 x to the first x1 over the x1 to x squared divided by 2r is equal to c squared over divided by 2r. Second offset bb the x1 and times x2 divided by 2r plus x2 squared divided by 2r plus 2 divided by 2r equals c squared over the r. Third offset cc x squared times x3 x2 times x offset third offset of cc x squared offset x second x third 2r with the x third to the 2 second power to the radius c squared over the r. Lay offset n the xn minus 1 xn x number the x number minus 1 times x number divided by 2r time plus x number squared 2r equals cc 1 divided by 2r plus cc1 squared over 2r equals c1 plus c distributed c1 plus c1 divided by 2r. The position of the tangent T1 with located at the measuring distance equal to the tangent length, the radius of the tangent, and the degree of it divided by 2 for the apex O. In this case, the angle of the deflection angle length of the E of the first chord is measured along with the tangent line T1, 0, and point A is marked. 0 end of the tape is played for the tangent point T1 with the swung of the arc of the end of A marked with the first offset with the measure with the value offset with the C squared 2R with the position point of it thus fixed. The chord T1, the chord tangent 1A is extended from the point B, A, B to marked with the second chord length equal to C. Position of the B is fixed on the curve with the sense of the value of the second offset with known as equal to C squared. The chord squared divided by the radius. Simple position of the points of CD and etc. are also located. So the last point where the curve is indicated is located between the value of the offset of the C1 C1 times C plus C1 divided by R with equals to C1 length with the last chord. Various points of the curve should be set with a greater precision because of any point that's fixed inaccurate is an error occurred forwardly all subsequent points. Or the Theodolite method. The Theodolite method setting out curves is a very popular mode of the Indian Railways, particularly when accuracies required for the method is known by the Rankines method of the tangential angle. The method is a curve that is set out using the tangent angles help with the Theodolite and the chain of type. The figure 13.7 lets A, B, C, and D and etc. be successful points for the curve length of T, measure 1A, X1, and AB, X2, BC, X3, CD, X4. That the OS 01, 02, 03, 04 with the tangent angle with the angles 01, 02, and A03 and 04, O tangent 1A, O tangent 1A, AT tangent 1B, tangent 1C, CT tangent 1D make successive chords among themselves. Let the triangle A, B, and 3 with the 4 with the deflecting angle with the chord of the deflection line. Alright, the Finite Method. Angle subtended with the center of the 100-foot chord, the diameter of the diameter, angle, tangent angle with the 100-foot chord, the diameter divided by 2, tangent angle with the x-foot chord, angle D equals D divided by 2 over times 100 times 1 divided by 100 equals the x degree. The 5730 divided by 2r with equals 1 divided by 100 is equal to 60 x minutes, and 1719 is x in radius. Where is the angle of the deflection in minutes for the x to the chord length of the feet? The r is the radius is seen as the angle, triangle 1, s, angle 1, angle 2, triangle 2 is s1, s2 equal to triangle 1 plus a angle squared, angle 3 with s1, s2, s3 equals angle squared plus 8, 3. Procedure valve with the setting of the curve valve with the theodolite set of the tangent point T1 in the direction of T2, tangent point 2O, the theodolite required with the angle 1 with which was already calculated with the tangent and 1 and 2 angle tangent 1 and A1 is set with no distance measured with the tangent 1 A1 in order to locate the point A. Now the theodolite rotated the deflection angle 2 is set with the direction of the tangent point 1B. Point B is located measuring AB with a chord length with x squared. Similar with the other points of CD is also located on the curve rotating the theodolite. Required deflection angles to the last point on the curve is reached. The higher precision is required for the curve can also be set by using 2 theodolites. Alright, superelevation. These following terms are frequently used for the design horizontal curve. Superelevation can the difference, or CA, the difference in the height between the outer and the inner rail with the curve that provided with the gradually lifting over the outer rail above the level of the inner rail. The inner rail is taken with the reference to the rail normally maintaining the original level of the inner rail. The zone at the gradient rail, the main function of superelevation found to ensure the better distribution of the load from both rails, to reduce the wear and tear of the rail's rolling stock, to neutralize the effects of the lateral forces, provide comfort for the passengers. Equal speed, whether the speed of the vehicle negotiating the curved traffic is such that the resultant force of the weight of the vehicle radial acceleration is perpendicular to the plane of the rails. Vehicles not subject to any unbalanced radial acceleration is said to be the equilibrium. The particular speed is called the equilibrium speed. Equilibrium speed is such that a speed in which the effect of the centrifugal force is completely balanced that can't provided. Maximal permissible speed, the high speed permitted the train on the curving taken on the consideration radius curve, the actual can't and the can't deficiency can excess length of the transition on the curve, the maximum permissible speed less than the maximum sectional speed of the section line. Permanent speed restriction becomes necessary. Can't deficiency CD is the curve of the train level to the ground. The curve, the speed higher than equilibrium speed, the difference between the theoretical can't required for the high speed and the actual can't be proved. Can excess or CE, the curve of the in the travel speed for the curve of the speed lower the equilibrium speed, the difference between the actual can't provided with the theoretical can reach for such a lower speed. The can't gradient and can't deficiency gradient include the increased degrees of the can't, the deficiency of the can't given length of the transition. The gradient 1 in 1,000 means that the deficiency can't is 1 millimeter obtained with loss of every 1,000 millimeter transition length. Rate of change for the can't deficiency, the rate of the can't deficiency while passing over the transition curve with the rate of 35 millimeter per second, but that means the vehicle is exchanging the changing can't deficiency of 35 millimeter each second with the travel of the transition traveling the maximum permissible speed. Alright, 3, 2, 1. Central figure of the force of the curved track of the vehicle. The tangent of the travel with the straight direction with the tangential curve. The even one, the move with the circular curve. The result of the vehicle that's subjected to the constant radial acceleration. Radial acceleration equals G equal to V2 V squared divided by R. V is the velocity minutes per second. The R is the radius of the meters. Radial acceleration procedure. Central figure which acts the radial direction away from the center of the value with the central figure force given in the form of the force equals mass times acceleration. Force equals mass times velocity squared per second divided by radius of the curve equals weight in grams over the velocity times the squared over the radius, where F is the central figure in terms of the weight, W is the weight of the vehicle in terms of the V is the speed of the meter, the G is the acceleration due to the gravity of the meter seconds, R is the radius of the curve of the meter. The counteract with the effect of the central figure of the force of the outer rail of the curve is elevated with a respect to the inner rail almost equal amount equal to superelevation. Equilibrium is reached in both end wheels exert special equal pressure on the rails. Superelevation is enough to bring the result in the central figure force with the force exerted by the weight of the wheel vehicle angle with the plane with the top surface of the rail within state of equilibrium, the difference height with the outer and inner rail curve known as equilibrium superelevation. Alright, equilibrium superelevation. Figure 13A of the angle of O is the angle, 0 of the angle of the incline with the plane with makes the horizontal line with it. Then tangent of the angle is equal to superelevation of the gauge or equal to E over the G. Also, tangent angle of central figure of force is equal to the central figure of force in tons over the weight. Real and these equations E is equal to over G with equal to force times over the weight. E with equal to the force times gravity over the weight, and E is equal to the weight over the grams divided by the velocity squared divided by times the rate divided by the radius times the gross. Gauge divided by the weight, and the gauge divided by velocity with the gauge divided by R, where E is the equilibrium superelevation gauge of the G is the gauge, V is the velocity, G is the small lowercase g is the acceleration due to the gravity, R is the rate of the curve of the metric system. Superelevation is given in the formula E is equal to G times V squared divided by 127 R, where E is the superelevation millimeter, V is the speed with the kilometers per hour, the radius of the curve of the meter, the G is the capital G is the dynamic of the gauge with millimeters, which is equal to the sum of the gauge and width of the railhead of the millimeters, the equal of the 1750 millimeters of the broad gauge track with a 1058 millimeter gauge. Figure 13A shows the superelevation of the weight, W angle, the O angle, the center of gravity, and the F. 1333, the thumb rules of calculating superelevation field. Field engineer can adopt the following thumb rules to determine the superelevation of any curve. Superelevation of the broad gauge in centimeters, speed in kilometers, hours divided by 10 squared times degree of curve divided by 13. For meter gauge value with the superelevation is taken 3/5 of this calculated using the preceding formula. Equilibrium speed in the formula. For example, the speed sanction speed is the section of the 100 kilometers an hour. The equilibrium speed is taken with 75% of the maximum sanction speed, known as 75 kilometers per hour. Superelevation 1 degree of curve calculated with the thumb rule as follows. SE is equal to 75 divided by 10 squared times 113 equal to 4.32 centimeters or 43.2 millimeters. Note the pressure of the maximum section speed of 100 kilometers an hour. The thumb rule is that for every 1 degree of curve, the can is approximately 43 millimeters broad gauge and 295 millimeters meter gauge. 13.2.4 equilibrium speed is provided with the superelevation. Amount of superelevation that is provided with the current depends on not only the maximum speed of the faster train, but also the average speed with a good traffically move with the section compromising. Therefore, it has achieved with providing superelevation away with the fastest train smoothing without causing discomfort to the passenger. Slow trains roughly safely without the fear of the derailment due to excessive superelevation. And earlier equilibrium speed is prescribed at the level of the track under average conditions when the maximum sanction speed of the section of the broad gauge meter gauge tracks over 50 kilometers an hour. 3/4 of the maximum sanction speed section was taken. The equilibrium speed subject to the choose the maximum between the minimum of 50 kilometers an hour, 30 miles an hour for the safe speed of the curve, whichever is less. Alright, when the maximum sanction speed of the section of the broad gauge meter gauge of the track was 50 kilometers an hour or 30 miles an hour less than the maximum sanction speed of the section of the safe speed of the curve, whichever is left is taken the equilibrium speed. Revised standard. The standard of deriving the equilibrium speed with the prescribed section that has been revived by the Indian Railways recently as per the revised standard of the chief engineer should decide the equilibrium speed that would require for the definite determination that can be provided with the curve with a careful deliberation taking into consideration following factors. Maximum permissible speed will actually be achieved by both fast train and good trains. Permanent and temporary speed restriction on the number of stoppage gradients and the composition of both slow and fast trains. After citing equilibrium is described the amount of superelevation provided by the calculation using the following formula. E is equal to G E squared over divided by 127 R is equal to 13.76 V squared divided by R for the broad gauge. 8.3 V squared divided by R for meter gauge, where the E is superelevation, M in millimeters, V is speed in kilometers per hour, the G is the dynamic gauge for the 175 millimeters broad gauge, 1058 millimeter gauge, and R is the radius for the curve of the meters. 13.25 maximum value superelevation. Maximum value superelevation has been laid down in experimental carried out with the European standard gauge for the overturning with the velocity taken into consideration track maintenance standards. Maximum value superelevation generally adopted with the round of the mainly waves around the world is 1/10 to 12th of a degree gauge. The value of the maximum superelevation prescribed in Indian Railways are given in 13.2. Maximum value superelevation broad gauge A group with 165 under normal conditions with the cat millimeter 185 millimeters. B broad gauge BC and DE. BC is 165 normal conditions 140 millimeters value of the cat. Meter gauge is 90 normal conditions millimeter cat and 100 with a special CE and permission CE. And natural gauge is 65 using a normal millimeter cant and 75 with a special permission CE. According to table 13T with the cant with 185 millimeter provided for the purpose of setting up the permanent structure of the side of the curve that had been laid anew with the construction said of the doubling of the group of the A root also have the potential for the allowing the increase of the speed of the future of the transient length, which should also be provided with the base for the cant 185 millimeter purpose of the planning and the laying of the curves. 326 the cant deficiency in the cant exact the cant deficiency of the difference for the equilibrium cant from the necessary with the maximum speed with the curve of the actual cant provided with the cant deficiency limited to consideration. Higher cant deficiency can cause the greater discomfort in passengers. Higher cant deficiencies leave the greater unbalanced central figure force with the turn to leave the requirement of the stronger tracks fastening with the sand with the result in greater lateral force. The maximum value of the cant deficiency prescribed in Indian Railways are given in 13.3. Broad gauge A and B, the minimal cant deficiency 75 for the both B broad gauge group. Broad gauge C and D and E has a 75 millimeter normal cant deficiency. A and B routes of 100 millimeter cant deficiency permitted on the nominated stock routes and approval of the C. Meter gauge has a 15 cant deficiency and 40 cant deficiency. Limiting values can accept the prescribed cant should be not more than 75 millimeters broad gauge, 65 millimeters meter gauge. Also, the type of the rolling stock cant efficiency should work out of the taking consideration all book with the speed with returning the trains running with a particular section. In this case, the section carried the predominantly good traffic. Access should be kept minimized aware of the inner rail table 13.4 with limiting the value of the various parameters of the curve. Minimum degree broad gauge 10, limited values is meter gauge 16, meter gauge and 40 narrow gauge. Maximum cant group A, B, and C 65 millimeters, group D and E 140 millimeters, 90 millimeter, 100 millimeters. Special permission of the chief engineer. Maximum cant deficiency in normal case for 75 millimeters, in special case 100 millimeter groups A and B with a nominated rolling stock with the permission of the chief engineer. Meter gauge 50 millimeters cant excess. Broad gauge 75 millimeters, meter gauge 65 millimeters. Maximum cant gradient 1 in 722 exemptional case 1 in 360 with the permission of the chief engineer within 1 in 720 and meter gauge rate of the change of the cant deficiency desirable 35 millimeters second at maximum 55 millimeters second. Broad gauge meter gauge desirable 35 millimeters second, measurable maximum 35 millimeters second. Maximum cant deficiency in the turnout 75 millimeters broad gauge, 50 millimeters meter gauge. Alright, 327, negative superelevation. The main line with the lines of the curve turn and counter with the picture of flexure of landing with the branch line. Superelevation necessary with the average speed of the turning the trains running with over the main line curve that cannot provide with figure 13.9b. 13.9AB with the out of the rail with the main line curve. The main must be higher than CD with the branch line. However, the CF should be higher than AE with the point C should be higher than point A. Those two contradiction conditions cannot be met without one layout. We must case the branch line curve with negative superelevation. Therefore, speeds with both tracks must be restricted, particularly on the branch line. Or you have AE with the branch line A and CE, CF with the branch line P with the fog, main line A, B, and C and D. Negative superelevation. The positive and negative superelevation branch line reduction speed over the main line calculated flows. The equilibrium superelevation branch line curve. The first calculated within the formula E equals GV squared divided by 127R. L equal superelevation. E is the equilibrium superelevation is the lowercase e produced the personal cant deficiency CD. The recent superelevation provided with this X equals N equal elevation times the cant deficiency minus the cant deficiency, where the X is superelevation and the equilibrium superelevation. Cant deficiency is 75 millimeters broad gauge, 50 millimeters meter gauge. Value of the cant deficiency is greater than higher than the equilibrium superelevation. Therefore, the normal degree, X is the normal negative. The branch line has a negative superelevation of X. The maximum permissible speed of the main line, which is superelevation of X, is calculated allowing the allowable cant deficiency X plus cant deficiency for the safe speed of the calculated smaller of the two values is taken in this maximal permissible speed of the main line curve. Alright, 13.3, safe speeds on curve. The electrical purpose of the safe speeds mean with the speed to protect the carriage from the danger of overturning the derailment provided with a certain margin safety earlier calculated empirical applying Martin's formula. Broad gauge and meter gauge transition curve of V is equal to 4.4 divided by the square root of R minus 70. V is the speed of the kilometers, the R is the radius in meters. Non-transition curve safe speed is equal to 4/5 of the speed of the calculating using the equation 13.7. Transition curve is equal to V equal to 3.65 to the square root of radius divided by 6 minus 6. Subject maximum 50 kilometers an hour. Non-transition curve's velocity is equal to 2.92 to the square root of R minus 6. Subject the maximum 40 kilometers an hour. The Indian Railway no longer follow the concept of safety speed for the curves on stipulation given here. Alright, 13.3.1, normal formula determining maximum permissible speed on transition curves. Earlier, Martin's formula was used to work with the maximum permissible speed, safe speed with the curve. Empirical formula has been changed with applying with the formula-based theoretical consideration per recommendation committee with the director, chief engineer, and the ACRS. The maximum speed with the transition curve determined the previous revised formula given velocity is the square root of CA minus plus CD. times R equals 13.76 equals to 0.27 CA, the square root of CA plus CD times R. V is the maximum speed in kilometers. CA, the actual cant in millimeters. CD, the most of the permitted cant deficiency in millimeters. R is the radius in meter. The equation derived in the equation 13.6, the equilibrium superelevation based on the assumption that G is 1750 millimeters in the center of the center distance between the railhead and broad gauge track of 52 kilogram rails. Meter gauge velocity is 0.4347, the square root of the cant, actual cant minus plus the cant deficiency divided by the radius. The base for the assumption of the center to center distance between railheads meter gauge is 1058 millimeters. Narrow gauge 762 minimum velocity of 3.65, the square root of R times minus 6, subject to minimum maximum 50 kilometers an hour. Or 13.3.2 nuclear activity to determine the maximum speed with the curve without transition. As the procedure that is being followed with the present determination maximum permissible speed with the curve, the transition involved with the concept of the virtual transition of the line. As the procedure with the valve with the present determination of maximal permissible speed with the curve with the transition over the concept of the virtual transition linear velocity train move with the uniform velocity straight track begin with the chain with the angular velocity assume with the first bogey reach with the tangent point change continue with the rear bogey reach with the tangent point with the movement of the train acquire with the full angular velocity the change with the motion with the train straight line to the curve takes place in the short distance between the bogey center with the consider with the virtual transition. Notice that the distance of 14.6 millimeters broad gauge and 13.7 meter gauge and 10.3 narrow gauge commencing on a straight line, half the distance between the tangent point terminating on the curve with the half of the distance being on the tangent point. The difference of the cant is considered as being gained over the length of the virtual transition. The cant has been to be gained in a similar manner with the aim. The cant gradient must not be steeper than 1 inch to the 360 and the broad gauge 1 in 720 and meter gauge. Narrow gauge under any circumstance the safe speed should be worked on the basis of the cant that can be particularly provided with the base of these criteria increase the permissible amount cant deficiency. In the case of non-transitional curve there are no cant provided with the safe speed but the curve can be worked by calculating permissible cant deficiencies after taking consideration of the rate which cant deficiencies gained or lost over the virtual transition. Maximal permissible speed of the curve. The maximum permissible speed of the curve is the maximum value with the speed calculated by determining the 4 different speed limits mentioned here. With the first speed, 3 speed limits are taken into account with the calculation. Maximum permissible speed, particularly in the length of the transition curve, is increased with the high speed route. However, the 4 speed route is always important as the cause may rise. Length of the transition curve can be altered easily. Maximum sanctioned speed with the section. Maximum permissible speed authorized with the Commission and Rail Safety determined after the analysis of the condition of the track, the standard interlocking type of the locomotive, the rolling stock use, other such factors. 2. Maximum speed of the section taking into consideration cant deficiency speed calculated with the formula given in table 13.5 with the first for the equilibrium speed desired with the taking the various factors with the consideration of the equilibrium superelevation calculated with the cant deficiency added with the equilibrium superelevation maximum speed calculated as per with this increase superelevation CA plus CD. Calculation permissible speed of the curves. First transition curve of the raw gauge velocity is 0.27 the square root of the R times CA plus CD, meter gauge V 0.347 the square root of R plus cant efficiency and cant maximum. For the narrow gauge velocity 365 divided by the square root of R divided minus 6 subject to the maximum 50 kilometers an hour. Non-transitional curve of the cant the virtual transition cant begins the virtual transition of 14.6 millimeters for the broad gauge 13.7 millimeter gauge 10.3 millimeter narrow gauge for the cant efficiency gradient is calculated early. Accordingly, the cant gradient is not to exceed 1 in 360 and 2.8 millimeters or meter divided by meter on broad gauge 1 in 720 or 1 in 4 millimeters a meter on broad and narrow gauge. Non-transition curves calculated permissible deficiency that is to be gained loss over the virtual transitions. The desirable value of the rate of the change cant deficiency 35 millimeters broad gauge 55 millimeters second of the meter gauge. Curves inadequate transition calculate the actual cant deficiency and provided with the taking the consideration limiting value. The cant deficiency has to run over the transition length with the rate of the exchange of the cant. The cant deficiency should not exceed the limited value with the broad gauge, the desired value of the 35 millimeter section, maximum permissible value of 55 millimeter section. 3. Maximum speed. Take with consideration speed of good trains and can't access for the can is calculated based on the speed of the slowing moving traffic. The good train with the speed that decide with each section, taking the various factors into account. Terminal value below 65 kilometers an hour. Broad gauge 50 kilometers an hour. Meter gauge maximum value of the can't access added to the can't. There should be the percentage sure, but the can't maximum speed does not exceed the value of the sum actual can't plus the can't access can't actual can't plus the can't access. Speed corresponding length of the transition curve. This is the lab value with the speed calculated with the taking the consideration various length of the transition curve given the formula 13.6. The following points of the may be used noted with the calculation maximum permissible speed of the curve. The criterion is to be used with the case only in the case of length of the transition curve to be increased due to the side restriction rate of the change of the cant and the cant deficiency to be permitted with the rate of 55 millimeters a second purely as an interim per measure of the existing curve of the broad gauge tracks. For a high speed broad gauge route, the speed restricted the result of the rate change of the cant deficiency exceeding 55 millimeters a second necessary to limit the cant deficiency value lower than 100 millimeters in such a way optimum result obtained in the situation the maximum permissible speed determined with the cant deficiency less than 100 millimeters but higher than the value of the maximum permissible speed. The concept is further explained with the help of the following solving the problems. Alright, when the rate of the cant is taken to the 35 millimeter section for the normal case, for the 55 millimeters exceptional case, the desirable length of the cant, the transition of the curve is cant times VM. V to V to the M or 0.8 10,000 G cam as V meters maximum trains with that. Are calculated superelevation maximum principal speed of the 2 degree of the broad gauge for the transition curve of the high speed with the maximum sanction for the speed of 110 kilometers an hour. The speed with the calculating equilibrium superelevation decided chief engineer 80 kilometers an hour. The book speed with a good strain with 50 kilometers an hour. Radius is equal to 1750 divided by D with the equal to 1750 divided by 2, 875 meters. Superelevation equilibrium speed is equal to G divided by V squared divided by 127 hour. But the G is 1750 millimeters. V is equal to 80 kilometers an hour. R is equal to 875. The superelevation 1750 divided by 80 squared divided by 750 times 80 squared divided by 127 875 with 188 millimeter 108.8 millimeters. Superelevation maximum sanction speed 110 kilometers an hour. GV squared divided by 127 hour with a 1750 times 110 squared divided by 127 times 875 190.6 millimeters. Cant deficiency 196.1 minus 108 89 millimeters, which is less than 100 millimeters. Hence permissible superelevation. Good trains book speed at 50 kilometers an hour. The GV is squared equal to 127 hours. 1750 times 50 squared times divided by 127 times 875 at 39.4 millimeters. Cant access for the might equals 108 minus 394 with a 61.4 millimeters, which is less than 75 millimeters. Hence the permissible maximum speed per potential speed safety speed for the curve is per theoretical condition. Iteration being high speed route. Velocity is equal to the square root of CA plus CA plus CD times R divided by sub 1376 or 0.27 divided by CA plus CD the square root of CA plus CA plus CD with the radius of the CA is 108 millimeters. The cant deficiency is 89.8 millimeters. Radius 87.5. 110.1 kilometers. The maximum permissible speed over the curve of the least the following maximum sanction speed of 110 kilometers an hour. The maximum safe speed of the curve based on the theoretical consideration 110.1 kilometers an hour. Also the non-constraint with the speed due to the transition length of the curve. The maximum permissible speed of the curve is 110 kilometers an hour with the super elevation provided with 108 millimeters, approximately 100 millimeters. Simplifying method for calculating permissible cant speed. Others often specified method for the calculating permissible cant with the maximum permissible speed of the field with the field specifies method for the applicable the most except these involve in a very flat curve. The calculating cant maximum section speed with the section set of 110 kilometers G for the standard formula C equals G V squared divided by 127 R, with this equals 6 C 110. Calculated the cant of 110 using the sum of the standard found with the slowest traffic. The good trains that can be made may be running at 50 kilometers an hour. This is C50. To do this, add the excess will become 50 plus CE. The cant excess the 50 cant equilibrium speed is used in the same standard formula at 80 kilometers an hour. The value of CE 80. Drop the lower three values obtained with the preceding step will become the permissible cant and CA. Three values of the C 110, C50, and CE with these and C80. Take the cant value, add the addition of these to maximum permissible speed using equation 1310. Alright, C10, C110 of the G times V squared, and, divided by 127 or 1750 times 110 times 110, 127 times 870, 196 millimeters. Can of 50 of the GB squared of the 127 R with the 1750 times 50 times 50, the 127, 875, and 394 millimeters. And odd end can access CAE plus CE that equals 39.4 plus 75, which is 114 millimeters. C8 can of 80 with the GV squared of 127 of the 750 of 80 times 80 of the 127 and 87.5 with 108 millimeters. Step 4, the lowest of the three values calculated preceding steps 108 millimeters. Therefore, 100 millimeters is adopted actual cant. Step 5 can be provided with a 100 millimeter cant deficiency of 75 millimeters, or 0.27 is the cant deficient cant actual and cant deficiency plus the cant deficiency plus times R equal to 0.27 of 100 plus 75 divided times 875 square root is 110.1 110 kilometers approximately. Therefore, the maximum allowable provided with the 100 millimeter maximum permissible speed of 110 kilometers. Calculate superelevation max permissible speed of the triangle length of the 3-degree curve with the high speed of the broad gauge section with the maximum sanctioned speed of 110 kilometers, assuming the equilibrium speed of 8 kilometers an hour, 80 kilometers an hour, kilometers an hour. Book speed with a good train with the 50 kilometers an hour. Radius curve is 1750 divided by D, 1750 divided by 3 with 583 meters. The equilibrium superelevation 80 kilometers an hour. The GV squared with 127 or 1750 times 80 squared with 127 times 583 is 151.2 millimeters. Superelevation maximum sanctioned speed 110 kilometers. 1750 over the 110 squared over the 127 to 583.3 is equal to 285 millimeters. Cant deficiency 285 millimeters minus 151 millimeters is 134.6 millimeters. Value cant deficiency more than 100 millimeters. Permitted value CD then takes in as thank you. Deficiency more than 100 millimeters permitted value of the cant deficiency. Therefore, the cant deficiency is 100 millimeters, known as the actual cant 285.8, and lower than 108.5 millimeters. However, the actual cant limited to 165 millimeters. Their values was adopted equal superelevation. Good trains should speed at 50 kilometers an hour. The 175 times 50 squared, 127 times 583. The 559 millimeters cant except for the actual cant 59 millimeters. 165 minus 559 106 millimeters. When excess of 75 millimeters permitted value of the 75 millimeters, take of the cant excess actual cant provided with the 75, 95, 59 millimeters, 134 millimeters. The cant is 135 millimeters provided with the rounding off the higher multiple of 5. 7. The safe speed potential high speed route with the cant excess cant deficiency and plus cant deficiency times radius square root. Square root of that divided by 1376 or 135 plus 100 times 583.3 divided by 1376. Square root. Maximum permissible speed for the curve with the least the following maximum permissible speed section 110 kilometers an hour. The safe speed with the curve 100 kilometers an hour. Maximal speed with the curve is therefore 100 kilometers an hour. The length of the transition maximum value among the following the taking the rate of the change with the conservation 35 millimeters a second. Length times 8 thousandths of cant efficiency cant and velometer speed with the 0.88 8 thousandths times 135 times 100, 108 meters. We're taking the rate of the change of the cant deficiency in consideration 35 millimeters a second. 8 thousandths the cant deficiency volt velocity meters 0.8 and 8 thousands times 100 times 100 meters of 80 millimeters. When taking cant gradient with a consideration 1 in 720, the leg comes with 0.72 super elevation, 0.72 with the 135 meters, 972.2 millimeters. Therefore, the super elevation provided with 135 millimeters maximum permissible speed over the curve of the 100 kilometers. Length of the transition is the curve of the 108 meters. All right, example 13.3.